So factorization of polynomials. So factorization of a polynomial, what that means is the following. That means expressing it as a product of lower degree polynomials. Expressing polynomial as a product of lower degree polynomials. That's what factorization means. Now we have an example above. We've just done one in a sense. Let's just look above, right? So let me zoom out a bit so we've got all this. So if I gave you this polynomial, this is a factorization of it, right? We're expressing it as a product of lower degree terms. Fantastic. Imagine though, if I didn't start from the top, I started from the bottom. How would I be able to go backwards? Well, that really is a thorny question. It's a question that you kind of know has to be difficult, even if you've never touched polynomials before, because it's already difficult for ordinary whole numbers. If I take some big whole number in the trillions or whatever and say, okay, write this as a product of smaller whole numbers, what are you going to do? Right? It's a really, really difficult problem. So it's no surprise that trying to factorize polynomials, write them as smaller degrees, is equally difficult, if not more difficult when it comes down to it. So I just want to make a warning here before we go any further. This problem is not something we can systematically solve. It's incredibly difficult in general. Very difficult in general. Very difficult in general. However, there are certain special cases that we should be aware of. Now, just to talk a bit broadly about this, one of the principal techniques for finding or for writing things, at least with linear factors, is to find zeros of polynomials and then to do long division. Now, that is not something I'm going to look at. It's not going to be really remotely important when it comes to the courses you're going to be doing in lower division. And as such, I'm not going to bother doing it. It's going to be something that I think you should be able to kind of do for sure. But if you're a bit rusty on it, you should know where to go, right? So for example, there are certainly online resources that explain this incredibly carefully. It's not really what matters when it comes to university level mathematics. So I'm not going to go through it because it'll take us too much of a tangent. But what is true is finding factorizations of quadratic polynomials is very important. So by far the most important case for the courses you're going to do is quadratics. So the most important case. So the most important case is the quadratic scenario. You can't really factor linears because they're already kind of broken up as far as you can go. So quadratic polynomials. Oh, I maybe should say as well, when I say factorization, I don't mean breaking them up as much as possible. I just mean breaking them up at all. So for example, if you take the number 40, a factorization of that is 4 times 10. But you could keep factorizing each piece. So for example, you could keep factorizing it. So 40 would be 4 times 10. You could write that as 2 times 5. That's for the 10 piece, and then 2 times 2 for the 4 piece, and then you can't really go any further. That's kind of a maximal factorization, if you want, where you've kind of broken it up as much as possible until essentially you've hit prime numbers. Factorization here, I'm not talking about doing it to the point you can't do it any further. That's terribly difficult. I'm just talking about breaking it at all. So here, in this case, this will be factorizable further, right? You'll be able to factor this a little bit more, I think. Doesn't matter. A factorization is some breakdown into a product. So it's just kind of a little thing to clarify. For polynomials, though, either you're factorable or you're not. And if you are factorable, you have to be broken up into the product of two linears, right? Which kind of is a maximal factorization. This is kind of special about quadratics. So I think we should do everything by example. There's no point in trying to do a general theory here. I want to do it by example. And I'm going to illustrate a few kind of crucial things about how to approach problems at the university level. So let's factorize this guy. So I'll write it in the format you're more familiar with. Let's do 2x squared plus x minus 1. So factorize this into linears. Now, it may not be possible. Not every polynomial can be factored into linears. This is something to be aware of. We'll talk about it in a second. So what I'm going to do is show you two approaches. Now, one approach is going to be a systematic approach, which will always work regardless of the polynomial, the quadratic polynomial. And I think it's very important that you have systematic approaches to problems, because there may be kind of fancy, elegant approaches which involve a little bit of guess and check or something like that, as we're going to see. But they may not work in general, or they may be very difficult to pull off. You always want to have a systematic approach to doing things. It's just an important thing, right? If your back's to the wall and you have to solve a problem in order for the rocket to take off without blowing up, you need to have a guaranteed method. So this is the systematic one. So this is inelegant, but it will always work. So the systematic approach. So the systematic approach is one you could teach to a computer, really. Okay, so first of all, let's assume I can be broken up. This isn't guaranteed to be true, but let's assume I can be broken up. So let's assume I can factorize this as follows. So I want to think a bit broadly about what it would mean to factorize. So I'm going to write this factorization in a very specific format. I'm going to write it as, so I'm going to pull the 2 out the front, because that's kind of the leading term, and then I'm going to write it as x minus alpha, x minus beta. So let's just take a moment to imagine that it's possible to do this. So this is a linear factorization where alpha and beta are constants. So we don't know what they are. So alpha and beta are constant. Okay, so let's think about some consequences of this. If this did happen, what would be true? So observe. Well, if this was equal to 0, so if this is equal to 0, this is, of course, if and only if 2 times x minus alpha times x minus beta is equal to 0. Now, this is if and only if. Well, what are the options? Well, 2 is not 0. So by the zero product property, either x minus alpha is 0 or x minus beta is 0, or both. If x minus alpha is 0, x would have to be alpha. If x minus beta is 0, x would have to be beta. So we are forced to have x is alpha or beta. So the zeros of this expression, the x which gives 0 as a number out, have to be alpha and beta if this is the factorization. And this really is the zero product. The zero product property. Okay, so all these simple things coming back at crucial moments. Okay, so what's the conclusion then of this? The conclusion would be if I'm going to factor this, so factorizing 2x squared plus x minus 1 is basically going to be the same thing as finding alpha and beta, which is the same thing as finding solutions to this equation. Okay. Now this isn't true for higher degree polynomials. You might have higher degree polynomials which are not going to break into these kind of linear pieces. So you can't do this logic. But for quadratics, it's completely correct, right? Factorizing is exactly the same thing as finding zeros. So now we're going to skip forward a bit and remind ourselves of kind of the brute force approach to finding zeros of quadratic equations. So let's recall the following. So I'm going to write this in standard format. If I have a quadratic equation, ax squared plus bx plus c, where a, b, and c are constants, this is if and only if x is of the following rather unpleasant form, minus b plus minus the square root. So if this is the first time you're ever seeing this, I apologize, but hopefully it's familiar. All inside the bracket there, or inside the square root, divided by 2a. Kind of pretty crazy formula. So this is called the quadratic formula. It's kind of a brute force way of finding zeros of quadratic equations. Now, at this point, I'm going to make an assumption. The assumption is I'm taking a square root there. And if b squared minus 4ac was negative, I couldn't take a square root, because you can't take square roots of negative numbers in the world of real numbers. So I'm going to make an assumption. If that did happen, it would essentially mean I couldn't factorize the polynomial. That's what it would mean. So there's no guarantee you can break it up. But I'm going to assume here that b squared minus 4ac is greater than or equal to 0. So we don't have any problems. Thankfully, that's the case in this situation. So let's use this to find, well, alpha and beta in this case. So hence, 2x squared plus x minus 1 is equal to 0 if and only if x is equal to, okay, so b is 1. So let me just make sure this is clearly labeled. So we've got a is equal to 2, b is equal to 1, c is equal to minus 1. So we're going to have to feed that very carefully into the formula. Minus 1 plus minus the square root, plus minus the square root of what? B squared, 1 squared, minus 4 times 2 times minus 1. All of that inside there. Divided by 2a, which is 2 times 2. So now we've got to do some algebra with radicals and this kind of business. So this is equal to what? This is minus 1 plus minus, okay, 1 squared minus minus 8 squared, it would be the square root of 9. All divided by 4. Thankfully, the square root of 9 is 3. So this is if and only if x is equal to minus 1 plus minus 3 divided by 4. Okay, so what's this? This is if and only if. We've got two options now. X is equal to, well, if it's plus 3, it would be 2 over 4. 2 over 4 is a half. If it's minus 3, it would be minus 1 minus 3 minus 4 divided by 4, or minus 1. Okay, so at this point, this, let's label, this is my alpha, and this is going to be my beta. So what's the conclusion? At this point, I can just go back to my original template, up at the very top here, and just feed that information in, and I have to be done. So the conclusion here is that 2x squared plus x minus 1 is equal to 2 times x minus a half times x minus minus 1, that's plus 1. So if you want to make this a little neater, it's up to you. You could bring the 2 into the first factor, 2x minus 1. There's no need to do this really. It just makes it look really nice with integers. So that approach will always work. It's a completely rock solid way of doing it. And the beauty of it is it also picks up whether or not it's possible. If up here this was negative, then I'd be taking a square root of a negative wouldn't exist. So there'd be no way of factorizing this, not in the world of real numbers. So this is a very strong method. It will always work. Now there is another method, which I'm sure you've seen, which is kind of more elegant, but does require a little bit more kind of staring at the sky and hoping some answers come to you. So here is the more elegant approach. That doesn't mean it's better. It just can be certainly a time save Okay, so it's an elegant way of doing it, as we're going to see. It's clever. It involves a clever piece of algebra that I'm not going to justify, but it does require a bit of intuition. So here's my polynomial, right? And this is, like I've written before, a is equal to 2, b is equal to 1, and c is equal to minus 1. So this approach involves basically finding two numbers with two very specific properties simultaneously. So we need to find two numbers let's say m and n with the following properties. So the first property is I want their product to be the same as the product of A and C. So mn has to be equal to 2 times minus 1, which of course is minus 2. So the crucial thing here is, in general, this would be A times C. That's the first thing I want to be true. And the second thing is I want their sum to be equal to B. B here is equal to 1. So m plus n is equal to b, and m times n would be a times c. Now, it's not obvious why this is important, but if you are able to do this, there's an incredibly elegant way to immediately write down a factorization, which I'll show you now, or pretty immediately. So this is the tough part about this approach. You need to be able to spot m and n. So first of all, there may be no m and n, right? It may be impossible, precisely because we could have a situation where there's no factorization, so no b squared, well, b squared minus 4ac is negative. So there may be no way of doing this. Bummer. But, at least not in the real numbers. But if you have this, and you're able to spot it, we can do something really clever. But spotting it's difficult. So can we spot it? So I want m times n is minus 2, and the sum is 1. Well, thankfully, in this case, there's a pretty obvious solution to it. M is 2, n is equal to minus 1. Works really nicely. It's kind of staring you in the face. This basically is just trial and error, though, or guess and check. This is the reason this is something you shouldn't rely on as much, in my opinion, not unless it's really obvious. Guess and check is a method you should only really use as a last resort, or if you have great confidence that it can be done quickly. So if you were confronted with this and you spent an hour trying to find an m and an n which does this, and you can't do it, just don't bother, right? Go use the systematic method, it will work. But this is kind of a good practice in understanding arithmetic, getting intuition for arithmetic. If you can do it fairly quickly, it's reasonable. So now at this point, you do the following. And this is probably something you've not seen before. It's a really elegant way to do this. So now split the middle term. So this is a really odd thing to do. It's not completely obvious why we're doing it, but let's take the middle term. So the middle term is b to the x, b times x. And we're going to split it as mx plus nx. Now we can do that precisely because m plus n is equal to b. Okay, so it's not obvious that this is a sensible plan, but let's see what occurs. So what do I get? I'm going to get 2x squared plus x minus 1 is equal to, okay, so 2x squared. So let's write the plus x as plus 2x minus x. Minus 1. So that's this is my this in this case. Okay, so why are we doing this? What's happening? Well, now let's do the following thing. Let's essentially bunch these two together and bunch these two together. Now the front two have a factor of x, so I can factor that out. So let's do that. In fact, let's take the 2x out, no harm there. So this is going to be x plus 1, is that right? Yes. Minus, let me tidy this up a bit, x plus 1 here. So it's minus x minus 1, it's minus parentheses x plus 1. And notice a miracle has happened. We have the same factor. The same factor has appeared. Awesome. Well, this means we can factor that out. So what do I get? Well, factoring it out, I get 2x. What is it? Minus 1 times x plus 1. That's just me doing the distributive property again. So this is absolutely fantastic, right? This has given me what? This has given me exactly what I have above. This here and this are the same. Let's zoom out to make sure that's true. Yep, they're exactly equal. So this approach is fantastic, right? It's ingenious. I'm not going to justify why it works. It's a very clever piece of algebra. It may be something you want to do yourself. But the main thing is it will always work if you can find an m and an n which do this. And that itself is difficult. So if you want to try to factor something quickly without going through the whole rigmarole of quadratic equation, that kind of business, I would say multiply a and c, try and find something whose product is that, whose sum is also equal to b, and if you can do that, then this is a pretty slick piece of algebra, right? It avoids the issue. But again, it requires spotting, and if you can't spot, forget it, right? So the most important thing as far as I'm concerned is without question understanding the systematic approach, because that will always work and it's something you can always rely on. It's very nice to understand this as well though, because it's a really useful method. And one of the nice things about this that maybe you haven't seen is it deals with a scenario where a is not necessarily 1. I think a lot of people have pretty good intuition for how to factor things where a is equal to 1. If it's not equal to 1, you've got problems. It could be quite difficult to choose what coefficients go at the front here. Right, that can be difficult. So this is a really nice way to do it, right? And I will also say in the special case where a is equal to 1, you can kind of do this much faster. You don't need to actually do, just to fit this back with maybe what you've seen before. A special case, if a is equal to 1, well, this actually implies that x squared plus bx plus c, you can just immediately go to this factorization, x plus m, x plus n, it's plus there. And if you FOIL this out, you'll be able to check that, right? The m times n will be the c, and then m plus n will be the b, and you'll get a nice 1 at the front. Something to say here though is this only works for a is equal to 1. It is not true in general that this kind of pattern fits, so this is a warning. So I'm really only telling you this to just show you that there's a kind of a bit of a shortcut for a is equal to 1, but a warning. It's a mistake seen people make in the past. So in general, it's not true, right? ax squared plus bx plus c is not equal to a times x plus m, x plus n. It's not that simple. It only works with a case a is equal to 1. If a is not equal to 1, you have to go through this procedure of splitting the middle term and then gathering. Okay, so my general warning about this is it's elegant, but it does rely on spotting an m and an n. If you can't do this, you should use the systematic approach without question.